Hey, some of you guys are watching this and are not subscribed. Please consider subscribing to the channel and let's get started. Have you ever wondered if you had pure coffee? Well, I did, and I had it near our yard, and I wanted to simulate what adulterated coffee would look like and then build two models. One, where I would predict if the coffee was adulterated, and follow that up with a secondary model to then estimate how much the coffee was adulterated. And I'll show you in this video how we can combine that using Python into a seamless two-step process. So we've been looking at coffee over multiple videos, and I want to refresh you of where we are. So first, we had built a classification model using a support vector classifier. And as you can see here, we did some data structuring, and we used a support vector classifier with grid search to optimize a model. In this case, we built a really great model. It had really good performance and was able to easily determine if we had adulterated coffee or authentic coffee. In the next video, I then built a regression model using a ridge regressor. And there, the data is also in GitHub, where we then estimated how much the coffee was adulterated once we knew that we were working with adulterated coffee. And now in this video, I want to show you how we can combine that. And so I want to create another data set where we can take advantage of both the classification, the labeled data, and the regression data, the quantitative analysis using our percent adulterated. And so let's begin by running this cell and running this cell here to set up the data. And so what I want to demonstrate is that we have a new data frame called all data. And if we look at it, it has a couple extra columns. We have an is adulterated column, which will either be 1 for true or 0 for false, as well as a percent adulterated column, in which case the first 5 rows are 21% adulterated. And if we sample so that you can see what more of this data looks like, we have several different columns. So I'm actually combining data from 2 different data sets to build this larger data set and just sort of help to power the study even more. Next, I'm going to create my standard normal variate. This is a common pre-processing step, as well as splitting my data into multiple different steps. So I've got my X data, my Y regression labels, which is the percent adulterated, and my Y classification labels, which is the is adulterated true or false, or 1 or 0 respectively. And of course, it's really important to then train, test, split. So you want to split out our training data that we're going to use to build these combined models, and then this test data that we're going to use to then validate the model. Importantly, by setting the random state to 42 in each of these cases, we will still get the same split, even though we're passing in 3 different arrays or data frames into this train test split argument. But this looks pretty good. And so again, I want to show you what xtrain looks like. You can see that we have a random subselection of our data. And then, of course, xtest is a smaller subsection of that from both our more recent coffee study and the older coffee study on multiple different instant K-cups. Let me get rid of this. Next, I want to set up my classifier. I'm going to use a support vector classifier with a C of 100, a kernel RBF, and a gamma equal to scale. And the reason I'm doing that is because I've already done the work in the previous video to determine what are the optimal parameters. And so I'm just taking these parameters here where C was 100, gamma was equal to scale, and kernel was RBF as part of how I'm setting up this current model here, as well as taking advantage of the work we did in the following video where we were optimizing the ridge, and in particular this alpha parameter to determine how much we want to regularize our variables. And so both of these have been set, and please check those videos out if you want to understand more about how we are leveraging SVC and this ridge regressor. So what I want to do next is fit both of these models to the respective training sets. Note, I am fitting the classifier to the class training data and the regressor to the reg training data. That's because I want to make sure that for the classifier that I'm actually fitting to the true-false labels, these categorical labels, and then for the regressor, I want to fit my quantitative variables. And so I want to split the data out and then fit the models individually. So this next cell, we have quite a bit going on, but we're essentially running 2 separate models. The first model is the classifier model, in which we will predict for xtest if we have authentic or adulterated material. And so I want to show you what that looks like when I run this line here. And let me print the output there. And you can see here that many of the values are coming back as adulterated. Now, in this video, we're not really going to focus again on how these respective models perform or optimize it. We've done that in previous videos. I just want to show you how we can now take this output array and pass in all the adulterated materials to the next model that's going to estimate by how much these materials have been adulterated. And that's what happens next. So next, I want to initialize an array to store our final prediction. And then we're going to go through our for loop, in which case we're going to loop through this list here, this array here. And if this predicted value is 1 or adulterated, it's going to pass that value to the regressor and then predict by how much that data has been adulterated. I've got a couple extra steps here to ensure that we are returning a frame because our model is expecting a wide data frame. So I have this 2-frame followed by a transpose step. And then we will store the final predictions into our final predictions list. Otherwise, we're going to append 0. So if the prediction equals 0, we're going to append 0. And that will be our final value. So when I run this and uncomment this line here, run this cell, you can see that our model is doing quite a bit of work for us. So the first sample came back as adulterated, and we can see that the true value is 100% adulterated. I am zipping the true value and our final predictions, and the final prediction is showing as 97%. The next value is showing as 70% adulterated, and our model is predicting 54%. In this third case, the model is saying this is an authentic material, and thus we're just returning 0. We're not going to regress this at all. And then you can see for the remaining samples, in some cases we were quite close, like this 90 being the true value and 95 being the predicted value. However, in other cases, we were kind of off. In this case here, we have a true value of 21% and a predicted adulteration of 4%. The same here. So these models definitely need more work to help us understand what's going on or enhance regularization through more sophisticated model frameworks. But you can see how we can combine multiple steps, multiple different models to do even more. So overall, you can see that this approach of combining 2 separate models, a classification model and a regression model, is not that complicated. However, these models do need a little bit more work if better accuracy is necessary, but I at least want to demonstrate what this workflow looks like. Lastly, let me know what other foods you want me to analyze. We've looked a lot at coffees. I'm going to start looking at oils. So I want to compare vegetable oil versus olive oil, and even understanding what happens to oil chemically once it begins to degrade. And of course, I'm going to be using a portable near-IR sensor to do that. And if there's other foods that you want me to test or other models you want me to attempt to build, let me know in the comments below. If you enjoyed the video, like, comment, subscribe, and I'll see you in the next one. Peace.